So yeah, just Kitsa and Harry and the only three that don't see here. There's only 2 desks though, or is there another empty desk I'm not seeing? Huh. Did somebody come that like maybe I don't notice anybody else that like wasn't on the list? No. Oh. All right. So again, chapter 9, it's going to be related to chapter 8. We'll still be using the unit circle. If you notice on the back of this front page, there's still a copy of the unit circle. We won't really look at the unit circle this week for much, but next week we'll start looking at it again. For this week, we'll be looking at more of these formulas on the front of this page. So it's a little overwhelming at first seeing all these formulas, but the ones we're going to use this week, or well, the first couple of days, are mainly just this top section here. So if you look at these formulas here, this section here, it's a lot of stuff we've already talked about. We just didn't really think of it in this way. This formula here is just basically saying that the sine of an angle is equal to the reciprocal of the cosecant. So like 1 over a number is the same thing as the reciprocal. So the tangent is the reciprocal of the cotangent, the secant's the reciprocal of cosine. So just kind of another way of writing it. But the way these formulas are going to work is we're going to be dealing with expressions and equations. And you're going to take an equation, and if you see something like sine over cosine, or you see like tangent is this, you can look on this page of formulas, and if you see something you can change something into, you can use these formulas to substitute like one thing for another. So in some equations in this chapter, you're going to start with a sine of theta, and you're going to turn it into 1 over the cosecant. So it's just replacing something with something that it's equal to, just to try to change the way the equation looks or try to simplify some things. So it's kind of similar, like if you had an equation and say you had like x plus 25 equals say 10 or something, and you just came along and instead of writing 25, you just change 25 into like 5 squared, since that's the same thing as 25. So we're going to be doing things like that, where you take something like, if you know sine is equal to this, like say you had like the sine of theta plus 2 equals something, you could change the sine into 1 over the cosecant of theta plus 2 equals something. So it's just changing something into something that it's equal to. On an equation like this, it wouldn't make much sense, but in some of the equations we're going to see today, you'll realize like why changing this into this might help you simplify the equation. So it's the same thing as changing like 25 into 5 squared. It's just, they're the same thing. It's just maybe if you see it in a different way, it might help you simplify an equation or something. So we're going to be doing that with these. These are some things we've talked about before a little bit, like tangent is equal to, on the unit circle, tangent was the y over the x. So that's another way of saying like the tangent is the sine over the cosine. So this one you'll use a lot. If you have a tangent in an equation, sometimes you'll change it into sine of theta over cosine of theta. So if that's that way, then it would make sense to the cotangent. You just flip it over. So the cotangent is equal to the cosine over the sine. And these ones over here, we're not going to use as much, but you'll see them a few on today's assignment. And then this group of identities here we'll use a lot in the chapter 2. These are called Pythagorean identities. It's these 3 here. They call them the Pythagorean theorem or Pythagorean identities because it's basically like a squared plus b squared equals c squared. So it's kind of like the Pythagorean theorem. Now these can be used a lot of different ways though. Like if you have the cosine of something squared plus the sine of something squared, it'll always equal 1. But you can always rearrange these things too. So like if I took away the cosine squared on both sides of this, so say I subtracted cosine squared here, subtracted cosine squared here, I would end up with the sine of theta squared equals 1 minus the cosine of theta squared. So you could add this here if you want. On the test and on the homeworks, you're going to be referring to this page a lot just because you're going to be like using these rules. You're going to not want to try to memorize all these, but by the end of the chapter, since you've used them enough, you're going to memorize some of these, but you don't have to memorize any of these for like your test or anything in this class. On the AP calculus test, you might need to have like this memorized by then, but you'll use it a bunch between now and then that it won't even be that hard to memorize. But these other ones, you probably won't memorize all these, but if you can just rearrange this formula into other forms, you could use this as an equation. Or say I took away the sine squared on both sides, then I'd have cosine of theta squared equals 1 minus the sine of theta squared. So if you're not seeing where I got these, I could show you really quickly, but you might not want to write this all over your paper. Just might make it a little bit messy. But like all I'm doing here is taking this and say I want to take away the cosine squared on this side, then those would cancel out. And then if I take it away on one side, I just take it away on the other side. So that's what I did. I took that away on that side and then got 1 minus cosine squared for that. So you could do the same thing with all three of these. You could write these in a bunch of different forms. This one says the tangent of an angle squared plus 1 will equal the secant squared. So you could like take away the 1 to the other side, and this would be that the tangent squared equals the secant squared minus 1. So I mean, there's all different forms you could write these equations in, and they would all be useful in different problems. So again, it's not going to make a whole lot of sense till we start using some of these today. But anybody just have a question, just confused on what I did on those, or just curious what I did on any of those? So again, all these is just going to be formulas you're going to use to try to simplify expressions throughout this chapter. So I'll kind of show you how it's going to work today, and then it'll take a few days till it really starts to make sense. Hopefully by Thursday, you feel pretty good after we leave class on Thursday. But today, you're probably going to feel a little bit confused most of the time. And maybe even when you're working on the homework today, you'll be a little bit confused. But hopefully you'll be able to pick out some of these and maybe figure out some of the problems on the homework, even if you can't figure them all out. So on the next page, this is some problems. If we had a lot of time, I would go through them. But I'm just going to skip pretty much everything on this page. But I just, instead of going over this problem, just try to copy down this example right here. And just to get the hang of working with these expressions, see if you can think what you would do if somebody said like to distribute this or to multiply this. Now, you've never done this before, so wouldn't expect anybody to know what to do with this, but just curious, what do you think you would do? What do you think you'd end up with as your answer if someone told you to distribute that? So part of this chapter, just getting used to working with these expressions, because it's not quite the same as just working with like X and Y. But this actually does distribute pretty much the same way as some simpler expression that might just have like X's and Y's. So when I see these expressions, and hopefully by the end of the chapter, you'll get there too. It's just something that takes a little while. But when I visualize this in my head, I think of this as like a simpler expression that I might have learned back in like 8th grade or 9th grade. That's a similar structure. So first, if you think you got a guess, maybe just take a guess. What do you think this would distribute to? But again, I wouldn't expect too many people to even stumble across the answer, and nobody would probably even know the answer for sure. But you might just guess and get it right. But if I see this, I kind of see something that looks like this, maybe like A times A plus B. So if I have to distribute something like this, if I know how to distribute something like this, it's going to distribute the same way. So you still might not be totally sure how it would look, but if you know how to distribute that, you should be able to distribute this the same way. So like a sine of theta is different than a cosine of theta, kind of like an A is different than a B. But if they're both sine of thetas, you could treat them both as like they're just A's. So you probably know on this, you could distribute this and get like A squared plus AB if you distributed that. So if you distributed this, you might have been thinking it's like sine, like this is going to be squared, but you might not be sure what to square. Do you square like the theta, or do you square the whole thing? Or so the way we write this is if we do like sine of theta times sine of theta, you could write that as sine of theta squared like that, since it's being squared by itself. So when you multiply that times that, that's what you'd get. Now, mathematicians they make a lot of shortcuts so that they don't have to write extra like symbols. So instead of having to write the parentheses here, mathematicians over the years started writing this like this. So they put the squared right there. And it's a little confusing at first, but once you start doing it, it gets pretty easy. But that right there just means it's the sine of theta. The whole thing is squared. So instead of putting parentheses around it and putting the squared, they just put the squared there to make it simple. So this right here just means sine of theta times sine of theta. It just means it's being squared. So you have to get used to that a little bit. It's different than if the theta was squared. If you ever saw this, you won't see this much, but if you ever saw this like that, that means that just this angle is being squared. And then you're going to take the sine of it. So that means something different. You'll barely ever see that. But if you see this, it means the whole thing is being multiplied by itself. And then to finish distributing, you do sine of theta times cosine of theta. So that would just be sine of theta times cosine of theta. And you can't really do anything with that. So that would just be part of the answer. So if you distribute it, you'd get that. Just like you get a squared plus ab over here. So these are the types of expressions we're going to be working with this week. And it's just, we're going to be doing a lot of the same math you've learned since like 8th and 9th grade, but we're going to be doing it with these kind of expressions. So it takes a little bit of getting used to. And then today, what we're actually going to be trying to do is take this and see how you can factor it back to this. So see if you had this as a problem, you might see something like this on your homework. If you took this, you'd want to be able to factor it back to this by like noticing that they both have a sign and you can take out the sign. So that's one of the first things we'll try to practice today. So if anybody's got questions on that, let me know. It's just kind of an introduction to get used to what we're going to be working with in this chapter. So on the back, we're going to just, I'll try to show you some simplifying you're going to do. The first kind of simplifying we're just going to practice is just factoring. So to be able to factor trigonometric expressions, you first need to just remember how to factor basic polynomials. So see if you had to factor these three up here. Do you remember how to factor those? So 3 is probably one you've been factoring a lot. Even this year, we've factored a lot of those. The greatest common factor is one you always want to keep in mind. That's just, if you look at any amount of terms, if they have a number, you can divide out of both of them. Or if they have a variable that's in both of them, you could take that out. So like 4x to the third and 6x squared, you could take out, it's like 2x squared. So that's just factoring out something that multiplies into both of the numbers or all three of the numbers. So if you multiplied 2x squared times something to get 4x to the third, that'd be 2x. So those would multiply to 4x to the third. Then you'd have to just think 2x squared times what would make 6x squared. So that should be a 3. So hopefully you remember how to factor those. That's just factoring out something they both have in common. Then a difference of squares is something you'll see a lot in this chapter too. That's where two things are subtracted and they're squared. That's when it always factors to one that's plus and one that's minus. And the first term in both factors is the square root of the first term of this. So whatever would multiply to 3x or 9x squared would have to be 3x times 3x. So it's going to be something times itself makes 9x squared. And then the last term in both will be whatever multiplies to y to the fourth. So y squared times y squared would make y to the fourth. So that's a difference of squares. You'll see a couple of those in this chapter. And then you might even see some like this, where this is where you could do that x kind of factoring and think what multiplies to negative 22 and adds up to 9. So that's going to have to be 11 and 2 somehow. So to make positive 9 and negative 22, the 2 must be negative. So this would be x plus 11 and x minus 2. So what you're going to try to do is try to do that same kind of factoring with trigonometric expressions. And it's going to look really confusing at first. It's going to take a little bit of getting used to. One of the weirdest things is like up here, we factored out an x. But with trigonometric expressions, you never factor out an x. So that can be a little confusing at first. So look at this first one, a. And I know it's the first one you've ever had to do this with, so wouldn't be expecting many people to actually see this right away. But see if you can think of something we can factor out of both of these. We have two things divided or separated by a minus sign. So it's kind of like up here where we had these two separated by the plus sign. And we thought, what's something we can divide out of this first one and this second one? So what's something we can take out of like this term right here and something we could take out of this term here? But it's a little different. You're not going to factor out an x because x is not like multiplied by these. So you can't just factor out x. You have to factor out like something more than just x. Does anybody see something you could factor out of those, you think? So you might think, can you factor out the sign? So, and then you might not be too sure how to do it. Can you just factor out maybe the sign? Or should you factor out the sine of x? So it takes some getting used to, definitely, but you factor out the sine of x. So if you notice that they both had sine in them, that's really good. So there's a sine multiplied in this expression or this term, and there's a sine in this term. So if I took out the sine of x, there's two things I could multiply the sine of x by. And if I distributed sine of x to this, it would give me this. So think about what would be left in there once you factor out the sine of x. So when I think of these, I try to think of this in terms of like simpler expressions. So when I see this, what I see myself is like a times b squared minus a. So when I see like the sine is kind of like one variable, the cosecant is squared, so that's like some other variable is squared, and then it's minus the sine again. So if I had this expression, I could factor out the a pretty easily. So if I had to factor this one out, I would factor out an a. Then if I took out an a from this, it'd still have b squared. And then a times something needs to be a, so that would just be a 1. So if you can factor out an a from this, use that same reasoning to factor out the sine of x from this. It just looks a little different at first, so it's pretty complicated to learn at first. But what would be left would be the cosecant squared, because sine times that would make this. And then sine of x times something needs to make sine of x, that would just be minus 1. So that's what you would do just to factor out the common factor. So again, it's just like factoring out the a over here. It's pretty easy when it looks like this, but it takes a little bit of practice with these. Does anybody have any questions about that? I know sometimes it's unclear, like why do we factor out the x? Why don't we take out the x from the cosecant? Or how do you know what to factor out? So part of it's just getting used to it, seeing a bunch of examples till you're really clear on how to work these out. So that's the factoring part. Now it says simplify each expression by factoring or substituting when possible. So we've never done any substituting yet, but that's one of the things we're going to do the most in this chapter. So if you want, if you want to keep it all together, I understand, but if you want to just tear off this first page too, if you don't think you'll lose it, if you have like a binder to keep it in, you could. But if you want to just keep flipping back to the front, you can. But to do the substitution, sometimes when you look at these, you'll recognize there's a way to change this into something else, or there's a way to change this into something else that would help me simplify this expression. So one thing you'll get in the hang of is if you see something with something squared and a 1, anytime you have something squared and a 1 in this chapter, there's probably one of these identities or formulas you can use to rewrite it as something else. So if you look at cosecant squared minus 1, and you look at this expression right here, this equation right here, it's not written as cosecant squared minus 1 equals something, but you could rearrange this equation to figure out what cosecant squared minus 1 equals. So what does cosecant squared minus 1 equal? There's something we can just change these parentheses to. Instead of having it be cosecant squared minus 1, we could rearrange this formula here to figure out what does cosecant squared minus 1 always equal, and then replace that with that right here. So again, it's not something I expect everybody to come up with right away. I'll show you how to do it in a second. Anybody think they see what I'm getting at, that we could just write right here in place of cosecant squared minus 1? So yeah, that's exactly right. This can be changed into just the cotangent of x squared. So if you're not too sure where that comes from yet, don't worry about it. You've never even seen how to do this yet, but a few people may have already figured that out, but I'll show you how that would work. But this is what we're going to be trying to do in this chapter, is if we see an expression that we think we can turn into something else, now we might be able to simplify this from here. So the reason, or the place that came from, is here. If you have cosecant squared and you have a 1 on this side, you could just take away 1 on this side and take away 1 on this side. If you take away 1 on this side, all of a sudden cotangent squared is all that's left. And then over here, it's cosecant squared minus 1. Now the variable doesn't matter. It doesn't matter if this is an x or a t or a theta. It still works. So now in our expression, we have this over here. So if this is equal to cotangent, that means we can just replace that with cotangent. Now why we would do that, it depends. If you think this might help us simplify this problem, that's why we would do it. If you're not too sure if it's going to simplify, you could just try it anyways. But I think most people would agree this looks a little bit simpler than that. So already we've kind of simplified it. Now we could go further. With these problems, it's kind of tough to know when to stop. So for now, just you can go until you kind of feel like stopping, or if you think you're as simple as you can get, you can just stop right there. If you might want to go further, you could see there's a way we can change cotangent also. So we've seen up here that tangent equals sine over cosine, and cotangent equals cosine over sine. Now, we don't have cotangent though, we have cotangent squared. Now, if I squared both sides of this equation, I would just end up with cotangent squared. And if I squared this side, I'd end up with cosine squared over sine squared. So that's another one you could add to this list if you want. I mean, you could add all different, you could make this cosine or cotangent to the third. These will both be to the third. It's probably not worth writing them all on there, but just knowing that if cotangent squared, that would be the same as cosine squared over sine squared. So we could actually keep going. We could change cotangent squared into cosine squared over sine squared. And then you might see one last little thing we could do. So if I change the cotangent squared into cosine of x squared over sine of x squared, there's one last little thing I might be able to do to simplify this. So if I thought of maybe this is like sine over 1, anybody see one last little thing you might be able to simplify here? So yeah, think about this like this. All you gotta do is think like the sine and the cosine are kind of like different variables almost. So this would be like a over 1 times maybe like b squared over a squared. So if you had that, anybody see something you could like reduce here or cancel out here? So if you have a over a squared, you should be able to reduce that. So you could even multiply this across if you need to, a over b, ab squared over a squared. But a over a squared, you could cancel out this with one of these because this would be like a to the first. So it'd be like b squared over a. So if you have sine of x over sine of x squared, you could reduce that if you want. So this could cancel out with one of these signs because remember sine squared is really just like sine of x times sine of x. So there's like 2 sine of x's multiplied right here. So if I cancel one of these with one of these up here, I'd have cosine of x squared over sine of x. So you could say that's the answer. Someone else might have just stopped right here and decided that's the simplest form of the answer. For these problems, there's no real way to know what's the most simplified form of the answer. So on your homework, just try to do a couple things. If you do a couple things and you stop right here, that's totally fine. If you keep going and you stop right here, that's okay too. So it's kind of confusing this section. When do you stop simplifying or when do you stop replacing things with something else? So you're just trying to get practice of what you can do. So where you stop is not too important. So you stopped here and then you check the answer in the textbook and it has this. Doesn't necessarily mean you did it wrong. Just means they may have done a couple more steps than you did. So just don't worry if you don't get the same answer in the textbook on all these problems. So that's the first one. It's kind of a lot in that problem. This one over here, this is just something to the fourth minus something to the fourth. So this is a difference of squares, kind of like this was up here. So if you factor this, you should be able to factor this to something plus something and something minus. So if you ever have two things that are squared and they're subtracted, the first term is just going to be the square root of this. So you got to think of something times itself that would multiply to secant of x to the fourth. So again, you haven't really done a whole lot of these, so kind of show you how this one would work. This would be the secant of x squared and the secant of x squared. So those together would multiply to the secant to the fourth. And then you might see what the square root of tangent to the fourth would be. So this would be tangent to the second times tangent to the second. It would make tangent to the fourth. So this right here would factor to this. And then when you look at these, anytime you see them that are squared, you might look at this row of identities called the Pythagorean identities, see if there's something you can use there. So it just so happens that tangent and secant squared are both in this equation right here. So now notice in here, we don't have tangent squared plus 1 or secant squared by itself in any of these, but we could actually rearrange this equation so that it matches what's written in one of these. So there's a lot of ways to do this, but there's one kind of fast way. So look, we have either secant squared plus tangent squared or secant squared minus tangent squared. If you look at this equation, there's a way to rearrange it so that you get one of those. So think, is it easy to rearrange this so that I get, what is it, secant squared plus tangent squared? Or can I rearrange this pretty easily and get secant squared minus tangent squared equals something? So look at this, see what you could do. And actually there's something you can get this to equal. So see if you can look at that expression here and figure out, using this relationship, what would secant squared minus tangent squared equal? Anybody think they see what secant squared minus tangent squared would equal if we rearrange this equation? Yeah, it would just equal 1. Because what do you have to do to get that to equal 1? Yeah, so if you just subtract this tangent squared to the other side, you could take away tangent squared here and take away tangent squared here, and you would just get 1 equals the secant squared minus the tangent squared. So that's another one you could just add to this list. There's a bunch of forms you could write this equation in. So if you're ever working in a problem and you see this equals, or this in your expression, you can just replace it with a 1. So secant squared minus tangent squared is 1. So this right here could just be 1. And then this, we can't really change anything. We can't really change this into anything. You could try it, but there's no way to rearrange this and get what secant squared plus tangent squared equals. It just won't work. So there's nothing to simplify this to, but that just simplifies to 1. So you could say this would be the answer. Now, again, you might try to go even further. You might try to change this into something or change that into something, but you can't always keep going with these. Sometimes it's just, you just got to stop there. But again, it's tough to know when to stop sometimes. So on the homework, I would just do 1 or 2 steps. And if you feel like there's not much more to do, you can just stop there. If you want to keep going and see what you can do with it, you can. Or you can just check the textbook answer, see like, did I get to the answer yet? Or do I need to keep going? So again, it's kind of just keep going until you think you're there, and then you can check the answers, see if you got to the final step you're supposed to get to. So that's that one. This one we won't see a whole lot in this chapter, but this is something you may see every once in a while. Now, this probably looks kind of strange to you guys. To me, it looks pretty like something we've been doing all year long, but I know the first time you see these, it doesn't look like that. So see if you can think. I'm saying this looks like something we've done quite a bit this year. It's a kind of factoring we've done. Does anybody look at this and like recognize maybe how they could factor that, or how that's similar to some factoring we've done this year? So when I see this, I see something basically like this. I see like I got something squared here. So I got something squared. I have 7 times that number. So like this is cosine squared. This is 7 cosine. So it's like x squared plus 7x plus 10. So when I see this, I'm thinking as long as I know how to factor this, I can factor that. So if you know how to factor x squared plus 7x plus 10, see if you can think how you would factor the one on the left. So this over here would just be x plus 5 and x plus 2. Now this one's not quite that simple, but it's almost that simple. See if you can figure out what you would have to change about this to make it distribute back to this instead of this. So like here, x times x would make x squared, and this is 2x, that's 5x, and that's 10. So over here, if I want to get cosine of x squared, I just need to put cosine of x and cosine of x, because those together would make cosine of x squared. And then if I just put the 5 and the 2, it'll actually work out just the same, because this will be 2 cosines of x, this will be 5 cosines of x, which will add up to 7 cosine of x, and then 5 times the 2 would make 10. So it's the same kind of factoring you've done before, it just looks a little bit different. So when you see something squared plus something times x plus another number, try to just think of it in the same way you factored these for a few years now, probably. So yeah, we won't see too many of those, but when they do come up, you can factor them the same way as those. Now, those ones are a little frustrating, the factoring and the simplifying, especially the first time you see them. These right here, these are the ones that are actually a little bit simpler. So we're going to do a lot of these in this week too. So see if you can start to see how these could work. So there's nothing you can factor on this. You can't factor out a tangent. I mean, it's really just one term anyway, so there's no way to factor one term. This is kind of just like a times b. You can't factor something times something else. Now, there's a way to use some of these identities to replace some of these expressions with other expressions, and you'll actually be able to get this to simplify down to something simpler. So you'll be able to turn tangent into something else, turn cosecant into something else, and then somehow you'll be able to cancel something and get this to be a simpler expression. So look just at this section right up here and see if you can pick out 2 of those identities in there, or 2 of those relationships you can use to change the tangent into something else, and then change the cosecant into something else. And then hopefully you'll get it to where something will cancel out once you've changed it into the other form. Now with tangent, there's always 2 choices. You can change tangent into this, or you can change tangent into this. So it kind of depends which one you think is going to be more useful depending on what else is in your problem. So you might want to wait and not worry about the tangent yet. Think about what can you change cosecant into. So based on this box I put here, there's only one choice for cosecant. It says cosecant is 1 over the sine. So the cosecant is the reciprocal of the sine. So let's just think, what if we change cosecant into 1 over the sine of x? So that's all we did was change that into that. So the cosecant is the exact same as 1 over the sine. Now, there's something we could change the tangent into, that if we change the tangent into it, it'll actually cancel out with something here and simplify into something simpler. So the tangent, remember there's two choices. You can change tangent into 1 over the cotangent or sine over cosine. So sometimes this will be the best one. Sometimes this will be the best one. Kind of depends on what else is there. Does anybody see already how, like, is it the cotangent one that's going to work, or is it the sine over cosine that's going to work? Yeah, so the sine over the cosine one will work. So you might be thinking sine because you see a sine in this one already. That's a good clue. If there's a sine in this one, it might be good to have a sine in this one. So if I change tangent into sine over cosine, since it's x, I'll just put like sine of x over cosine of x. And then think if we multiplied those together, anybody see what that would multiply to? So yeah, you could cancel the signs out right away. Yeah, sine of x over sine of x is just going to cancel out. So if the sine of x is canceled out, all that's really left is 1 over the cosine of x. And then you could leave the answer like that, but if you look in the textbook, they would even change that answer. So think about, what do you think they would write 1 over cosine of x as? So there's something on here that tells you what 1 over the cosine is, or you just know the cosine is the reciprocal of the secant. So if you have 1 over cosine, they would just say the answer would be the secant of x. So the tangent of an angle times the cosecant of an angle will always equal the secant of the angle. So we simplified this expression down to just one expression, or one ratio, or one trigonometric function here. So we had two, and somehow we were able to rewrite them in other forms and get them to simplify down to that. So this is something we're going to do a lot in this chapter. Once you get the hang of it, it's kind of fun. Sometimes there's like a puzzle. Sometimes they'll give you like 5 or 6 of these in a row, and you got to figure out how to change them all to get everything to cancel out and get it down to something simpler. At first, it's kind of frustrating, but once you get the hang of it, some of these problems can actually get kind of interesting. Probably by Thursday, you'll hopefully even like enjoy doing some of these, even though I know the first day that sounds kind of crazy, that you might actually enjoy this. It's pretty overwhelming at first. So try to do maybe just one more of these really quickly. This one down here, F. So if you look at F, kind of a long expression, a lot of letters, a lot of exponents, a lot of variables. Pretty overwhelming to look at that at this point. But by the end of this year, hopefully you'll see expressions like this and not get too overwhelmed by it. You'll be able to kind of just calmly look at this, kind of break it down in your head. What do you notice the structure of this is? What might you be able to do with an expression like this? So when I see this expression, I see something kind of like this. I see something to the third right here. So maybe that's like a to the third plus, then it's the same sign. So that's like an a. This is like cosine is like a different variable almost. So that'd be like b squared plus, and then there's another a. So like every time there's a sign, I think of that's like one variable. Every time there's a cosine, that's something else. So if I had that expression, I mean, it's not a simple expression, but I could factor out an a from this. So if I had this expression, I would probably factor out an a, and then I would end up with something. So see if you can see what would happen if I factored out an a, what I would end up with. But in that case, think about what am I really factoring out of this? So what is it that all 3 of these terms have? So there's a term here, and a term here. So all 3 of these terms have a sign, at least one sign. So I could take out a sine of x. So if you take out a sine of x from all 3 terms, see if you can figure out what would be left. So you're going to have, or I guess I could have left a little more space for that first one. But there's going to be 3 numbers left inside of here if I take out the sine. There's going to be something here to make sine to the third. Something needs to be here to multiply to sine times cosine squared. And something needs to be here to multiply just to sine. Let's see if you figure out what would be left in there. So again, this takes some getting used to. This means sine to the third power, basically. So if this was x to the third and you factor out x, there would still be x squared. So if it's sine to the third and you factor out sine, there'll still be sine squared of x or sine of x squared. And then if I take out the sine from this one, all that's left is the cosine squared of x there. And then at the end, sine of x times something has to make sine of x. So this would just be a +1. And so that's just factoring out a common factor. That'll get a little easier as you practice it more. Then what's left, there's always a lot of things you can do from here. So you just kind of look, is there anything I can replace? Is there anything I can substitute something? Now, there's really a lot of things you could do, and that's where it gets kind of frustrating at first, because at first you're not going to notice the easy things right away. So it takes a little bit of practice to really notice like what's the best thing to do next. But there is something really simple on here if you look at these Pythagorean identities. So anytime you see like sine squared and cosine squared in the same expression, you'll probably get used to recognizing that it says here sine squared plus the cosine squared always equals 1. So anytime you have sine squared plus cosine squared in an equation or in an expression, you can just change that into a 1. So this right here, sine squared plus cosine squared, just equals 1. So the sine of x on the outside, there's nothing we can do with that. But anybody see what's going to be left in the parentheses now? It's not super easy to see. Well, what would the parentheses simplify to? It should simplify to a simple number. So yeah, it should just simplify to 2, because sine squared plus cosine squared equals 1. So this is just 1 plus 1, which would make 2 in here. So this would just be like sine of x times 2 is what that would simplify to. So in this chapter, in this class, we're not really even going to see why you would use this. It's just practicing a skill that you'll use in calculus. Because in calculus, you might have to work with this graph here or this expression here, but knowing that you can just change it into this would be a lot easier to work with than this. So it's just practicing and simplifying. It also gives you a lot of practice just with all the skills you've learned so far in high school, like factoring and adding and subtracting fractions and solving equations, things like that, and multiplying things like this and canceling things out. So it's a lot of practice with just basic algebra skills that you'll need in any like college math classes you take. And then it's a lot of practice with stuff you'll use for calculus too. So again, this simplifying something you'll use in a calculus class, but all these algebraic steps are just stuff you'll use in any math class. So there's a couple other sections of identities on here. I don't usually use these as much, but the textbook uses these a little bit. These ones are usually pretty quick to pick out, but if you ever see something with like pi over 2 minus theta or like a negative theta, you could use like these called the cofunction identities. So it's just the sine of this angle is always equal to the cosine. So these identities just are talking about two angles in the same triangle. So like if theta, if you're in a right triangle, if this is theta, this is just going to be like 90 degrees minus theta, because that's just the way right triangles work out. So 90 degrees is the same as pi over 2. So all it's really saying is like the cosine of this angle is equal to the sine of this angle, which would make sense because the cosine here would be like this side over this side, and the sine here would be this side over this side. So that's all it's really saying is the cosine of this angle is the same as the sine of that angle, or the sine of this angle is the same as the cosine of that angle. That's all it's really saying, but these are just expressions you can use to simplify other ones. So if you have like this one here, the tangent of this times the sine of this, the sine of theta, there's probably not much you're going to do with that. I'll just keep that there for now. But the tangent, you could see pretty easily on here. You can change the tangent into cotangent. So the tangent of this equals just the cotangent of the simple angle. So I would just change that. That's pretty obvious switch to make because there's not much else you're going to do with that. It's pretty clear. It just looks like that. But then from here, you can kind of get creative, see if you can think, what can you do with maybe changing this or changing both of these to get this to simplify? So this simplifies actually down to just one simple trig expression or trig function. So see if you can start getting creative. Again, it takes some time to get good at this, but the more you do these, you'll get a little bit faster with these. Does anybody see something they can change one of these into? It might help this simplify. So sometimes you'll change both of these. In this one, I would just recommend there's only changing one of these. So if you change just one of these into something else, you should get something to cancel out. Yeah, it's really good. Yeah, so again, you'll start to pick these up better as you practice more, but some of you guys are already picking this up pretty fast. But again, if you're not picking it up as fast as Zayden saw this one, that's fine. You'll get the hang of it as you see more of these. But again, you just want to kind of get, I don't know, creative. You just want to like think, what are all the options I could do here? The more you practice them, the more you'll see the better options to pick. But yeah, cotangent is equal to cosine over sine. So anytime I see cotangent in an expression, I can change it into this. So if I just change cotangent into cosine of theta over sine of theta, then think about why we might have done that now that we see this. Sine of theta is like the same as sine of theta over 1. So a sine of theta over sine of theta, those will just reduce to 1. And then this will just multiply to cosine of theta. So if I took the tangent of an angle minus, or pi over 2 minus an angle times the sine of an angle, I would always get the same answer as if I just took the cosine of the angle. So if I plugged in like 30 degrees here and 30 degrees here and did all this, I'd get the same thing as cosine of 30 degrees. So that's just what this says, is that this simplifies down to this. So yeah, we had to do a couple things there, do a couple of substitutions there. So we haven't done any with negative angles yet. This is this section down here, opposite angle identities. So this is just a relationship that always ends up being true. And you can think about the unit circle if you want to think why this works. This is just saying like the cosine of negative 30 degrees is the same as cosine of 30. So you might think on the unit circle why that works, because like 30 degrees is up here, negative 30 would be down here. They both have the same cosine. So that's a relationship that's true. Sine, they say, is an odd function, because if you did like the sine of 30 degrees and the sine of negative 30 degrees, these would have opposite signs. So the sine of negative theta is the opposite of the sine of theta. So it's not quite as simple. And then tangent is kind of the same as sine. It's the tangent of negative theta is equal to the negative tangent of theta. So for this chapter though, you just need to know how to like replace those. So cosine of negative theta, you could just turn that into cosine of theta. So the negative basically is irrelevant with cosine. So that doesn't make a difference. But the sine of negative theta is not just sine of theta. It's not that simple. The sine of negative angle is the opposite of the sine of the positive angle. So this would be negative sine of theta. So there's nothing we need to like cancel out or change cosine into or sine into, but there's something we can just say this equals. That's a little bit simpler to say. It doesn't involve a fraction. So think about what might we say cosine over negative sine would equal. So it's nothing exactly that's on your page. Now, if you remember on the last one, Zayden remembered cotangent's cosine over sine. So what do you think we'd say cosine divided by negative sine might equal? Yeah, very good. Yeah, cosine over sine is cotangent. So a positive divided by a negative is just going to be negative cotangent of theta. So that's what that one would be. So again, this is the first time you've seen any of these examples. So the more you see them, the more you practice them, you'll start to get better at seeing some of these. But so you can start to pick up some of these. So this one, sine of negative theta, we just did that one. So I'll just copy that down. Sine of negative theta is negative sine of theta. So basically on sine, the negative can just come out to the front. With cosine, the negative just goes away the way cosine works. Now this right here, 1 plus the cotangent squared. So anytime you see a 1 and you see something squared, you should probably think about this row of identities here in the middle, sort of. So I don't know if we've written this one down yet. Actually, yeah, this one is exactly one that's on your page. So look on here, see what 1 plus the cotangent squared is the same as. So 1 plus the cotangent squared is just the same as the cosecant squared. So it's the one that was already printed on the page. 1 plus cotangent squared equals the cosecant squared. Now you might just stop there, but cosecant can actually be changed into cosecant's the reciprocal of sine. So we haven't had to do one of these that's squared yet, but just if you think about it, if you square this side and you square this side, you would get cosecant squared and 1 over sine squared. So these work if they're squared also. So you can just add that or just know that these work if they're squared as well. So cosecant's 1 over sine, but cosecant squared would be 1 over sine squared. So cosecant squared can be 1 over the sine squared. And then this is times negative sine over 1, you could say. So that's not the simplest thing to reduce, but sine over sine squared, that's like x over x squared. You could cancel out one of the signs on top. This is like sine times sine. So one of these signs would cancel out with one of these signs and it wouldn't be squared anymore. So this could be like negative 1 over the sine. And then 1 over sine, you could always, it's always good to not write things as fractions if you don't have to. 1 over sine is the same as cosecant if you take off the squared. So 1 over sine, this would be like negative cosecant of theta. So all of this right here would just simplify down to that if we did all of those steps. So D is pretty similar to A, so I'll just skip that one for now because there's a few others I want to try to get to. But hopefully you're starting to get the hang of this. I know it's really overwhelming the first day of this. And once we get into what we're going to do on Thursday, it'll get a little bit easier. So the problems will get a little bit easier and you'll just get more familiar with this. So I know it's always a frustrating like first lesson. It's a lot to take in. If you're trying to pay attention to every single example, you've probably got a little bit of a headache right now. It's a lot of little details to try to take in, a lot of things to put together. So I know how it is. It's a tough first lesson to start this chapter, but it'll all start to like come together more as we go through this week. Hopefully by Thursday, you'll feel a little bit more comfortable doing these. So there's a few pages out of the textbook to try for homework, and then there's a few pages or a few problems on this next page, but just want to try to go over a couple other examples today, and then we'll finish some of these on Wednesday. So another thing we're going to use in this chapter, sometimes you'll distribute, sometimes you'll be adding fractions. So just want to go over these really quickly and then try to do maybe 1 or 2 more examples. But if you had something like this, you could distribute this just like anything you learned back in like 8th or 9th grade. Like you could do the FOIL method if that's what you learned, but like 1 times 1 is just 1. Then this would be 1 times negative sine of x. This would be positive sine of x times 1. And then sine of x times itself is like sine squared of x is what they say. But a positive times a negative would just be negative. So if you distributed those, the negative sine of x and the positive sine of x cancel out. So this is just 1 minus the sine of x squared, or the sine squared of x. So this and this are the same thing. But you could also change this into something. Anytime you see an expression squared and you see a 1, you'll eventually start to remember this row of identities here. So 1 minus the sine squared, I wrote this down earlier, just equals the cosine squared. So you could change this into the cosine squared. Or you could leave it like that. Either one would be fine. But cosine of x squared would factor down to that if you broke it down. So again, it's just a little more practice getting used to these. Another thing I just want to review really quickly is how to add or subtract fractions, because you're going to do that a little bit in this chapter. So if you did good in chapter 6, this was the first chapter we did this semester. Some people didn't quite ever really do very well with adding and subtracting fractions, so you'll get a little more time to practice those in this chapter. But if you're still confused how to get a common denominator, make sure you practice that. So to add or subtract fractions, I'll just skip this one because it's easy. But if you need a common denominator, you need to think of something that both of the denominators multiply into. So like this one, 2 and 6, I could use 12. Or I could just use 6 because they both multiply into 6. But one has x and one has x squared. So I could multiply them and use x to the 3rd. Or I could just use x squared because both of these numbers can multiply to 6x squared. As long as I multiply this one by something. And whatever I multiply on the bottom, I just have to multiply on the top. And then I have to multiply this by something on the top and the bottom to get 6x squared on the bottom. So it's just a really quick review before we try to do this with sine and cosine. But if you got any questions, if you want me to go over slower how I got the 6x squared, let me know. Or yeah, that's fine, Cassandra. Yeah, I'll record this. You can watch the last part that you missed if you have time later. So this right here, this one I need to get multiplied by 3 to make 6x squared. So I multiply the top by 3 and get 9x. And then this would just need to get multiplied by x to make 6x squared. So I'd multiply the top by x and get 4x. And then once you get here, you just add the top and then keep the denominator the same. And then you could reduce the x's. So you could reduce this to 13 over 6x. But the main part to see is how to get the common denominator. Just remember how that works. So if you never really learned that in chapter 6, you want a little more review on that, just let me know at the end of class, or let me know in the office hours today. I can help you practice some of that more when it comes up. But just want to try to do maybe 2 more of these, or maybe we'll just do, I'll try to do these 2 quickly, and then maybe have a few minutes to try some on your own on the homework. And then we'll finish the rest of these on Wednesday. So there's a lot of methods to simplify things. So this is like what some textbooks would recommend, like try to factor things. You could try to rewrite everything in terms of sine and cosine. So that would be like using these identities to try to change everything into sines and cosines. Or you could rewrite all terms in the form of the same function. So that just means like make everything like all sine, or like make it all like cosine, or whatever it is. And then you can combine terms if possible by adding fractions. That's something we'll try to practice. Or number 5 we'll get to on Wednesday. So this one here, if you had to factor this, it's cosecant squared and it's got cotangent in it. That's like having like x squared minus like y minus 3. But you can't factor x squared minus y minus 3. So if these aren't the same, the cosecant and the cotangent aren't the same, you can't factor this. But the cosecant squared, you could change the cosecant squared into the cotangent squared plus 1. So if this is a cotangent and cosecant can be turned into cotangent, you could use this to change cosecant squared into cotangent squared. So, I'll do this one kind of quickly. So this would turn into, this right here would just turn into this. And then it would still be minus cotangent of x minus 3. So that's just one of the identities. What's good about that is not everything's in terms of cotangent. So if I just combine the 1 and the negative 3, I'd end up with cotangent squared of x minus cotangent of x. And the plus 1 and the minus 3 will be minus 2. And then from there, you could try to factor this. So this would factor just like, think of this as like basically like x squared minus x minus 2. So if you see this, try to think of it like that. If you know how to factor this, you could factor this the same way. It's just instead of x and x, it's going to have cotangent of x and cotangent of x. So you're just thinking of 2 numbers that multiply to negative 2 add up to negative 1. So it's a little confusing looking at it this way, but if you can factor maybe this first, then it might help you. This would be like x minus 2 and x plus 1. This would be like minus 2 and plus 1. And then sometimes you can go further from there, but for this one, we'll just stop there. I don't think there's much else useful you can do on that one. So yeah, that's pretty complicated one. We might practice some of that on Wednesday. I want to just do one of the next one because this is something we'll use a lot in this chapter. So yeah, I know it's been pretty overwhelming, I'm sure, today. Just try to just collect your thoughts really quickly. Just try to focus on one more example. And then maybe if you got some energy left, you can try a couple on the homework. But really just try to focus on one more of these, and then we'll practice some more of these throughout the week. This one, you have something plus something. This one, we're actually going to be able to add these 2 together. But to add them together, we need to make at least one of them a fraction or make both of them a fraction. So what I'm going to do is probably just keep the first one as cosine of u. You could change cosine into like 1 over the secant, but we'll just leave it like that for now. But I want to change this into tangent. I want to change the tangent into sine over cosine so that I can combine it with this sign. So tangent is always the sine over the cosine. So you'll get hang of that pretty quickly. You'll kind of memorize that one pretty quickly this week if you haven't already. But tangent's the sine over the cosine, and then times the sine. We'll just keep the sine the same. So all I've done so far is change the tangent into sine over cosine. So that's just using this one that we've seen a couple of times today. And then I can multiply these together. So this is like sine over 1. So when you multiply fractions, you just multiply across the top and across the bottom. So the first expression or first value is just cosine of u. This is going to be sine squared of u over cosine of u. So I know I kind of connected those. But see if you got any questions how to get to there so far. And then the last thing we're going to try to do is get a common denominator here. So with numbers, it's hard enough to get a common denominator. Sometimes with all these letters, people get even more confused. But this one, the common denominator is actually kind of simple. I know it's not a number, so that always makes it harder. But anybody see a common denominator we could actually get both of these fractions to have? Yeah, it's kind of strange. You've never added fractions with the denominator like this before. But there's kind of a simple way to get a common denominator on these two. And it's pretty much the same way you would do it anytime you have something over 1. If you have like 5 over 1 plus, say, 7/13, like what denominator could you use for those two? So nobody knows a common denominator they could use for these two fractions. Yeah, you could use 13, right? Like I could just multiply this by 13 over 13 and they would match. So if one of the denominators is 1, you could just change this denominator into this one. So I'm just going to keep the second fraction the same. Keep this sine squared of u over cosine of u. But I'm going to try to change the first fraction so that it also has cosine of u as the denominator. So that's kind of the last tricky thing you got to figure out. What would this fraction be if we change its denominator? So I'm going to multiply something here and something here and get the same denominator and then try to add these together and see if you can keep working on this. There's a way to get this to equal, let's see, this should equal the secant of u if you can get it all the way to the end. So see if anybody can figure out how I can go from here just down to that. There's a few more steps. But if you can figure out how to change this denominator to cosine, and then you can remember one other thing we've used today a couple of times, you might see how I can get this whole thing just to equal secant of u somehow. If you can do that, that's pretty good for the first day. But if not, I'll show those steps in just a second. But anybody be able to get secant of u, I think? Yeah, a couple of people nodding their head. That's pretty good if you can get secant of u from here after just seeing this for maybe an hour or so. But again, I wouldn't expect everybody to get there yet, but maybe by Thursday, everybody can see how to do this. So to finish this, you need to get the denominator to be cosine over here. So I need to multiply this by cosine of u and multiply this by cosine of u. So again, it's a little different not using numbers to get common denominators, but it's pretty similar if you've done it with variables a lot. But I know it takes a little getting used to. This would be cosine of u times 1 is cosine of u. And then cosine times itself, that's when we put the squared like right there. So that's cosine of u squared. Now if you add these together, it's going to have the same denominator. So it's just going to be something over cosine of u. But it's cosine squared plus the sine squared. And then you might be thinking, how the hell am I going to get that to equal that? I mean, there's a lot there. But there's something pretty simple you can do in this to get it down to here. We've used it a couple of times today. And it's one, again, as you do this more, you'll pick it out more quickly. But cosine squared plus sine squared, anytime you have that, it equals 1. So cosine squared plus sine squared or sine squared plus cosine squared equals 1. So this really just equals 1 over the cosine of u. And 1 over the cosine is the same as the secant. So yeah, you got that there on your own. That's really good. That's the first one you've seen of those, though, so I wouldn't expect anybody to get that as one example. So we'll try to do a few more examples on Wednesday. Like we'll try this one here, try to get a common denominator and add those. But otherwise, you got about 20 minutes still, I think, right? Yeah. So there's 2 sections of homework for today, just to give you a bunch of problems to practice. There's, if you flip ahead a couple pages, there's this homework 34. You might just start with that since you have the packet out right now. And then there's like 8 problems out of the textbook that are similar to these to practice too. Now the textbook, you can check the back of the book for answers or look up the answers online. These, I'll post the answers maybe later on today, just so you can check if you're on the right track on some of these. Now, I wouldn't expect you to get all these right today. We haven't even had time to go through all the examples. So you might even see some we haven't even gone over an example of yet. Like especially some of these on the next page. But everything on this page, we've kind of done something similar to it, maybe at least the first row and some on the second row. So see what you can do with some of these to just change some of these into something else, get things to cancel out or get things to reduce. See what you can get these to simplify too. Again, they might not all be very easy. You might try something and it makes the problem more complicated. That happens a lot. If you try something first and it just makes the problem look harder, you might just want to start over with something else. So sometimes that has to happen. Sometimes if you just keep going, eventually it'll simplify. Sometimes you can just keep going and keep making the problem worse and worse, which is normal. It doesn't mean you're doing something wrong. It just means you're not like picking out the easiest way to do it. So like if I change secant into like, I don't know, if I change, I guess this one, there's only really one way to do it. So if you change secant into something else or change cosine into something else, should be able to get that one to simplify pretty easily. But this one, if I change tangent into 1 over cotangent, that's not wrong, but it won't help me solve that problem. So I might make this problem more complicated if I do that. But if I change tangent into something else, I could probably simplify that one. So see if you can figure out the first two, because if you get stuck on either of the first two, probably want to get some help before you leave today. And then if you can get even 3 or 4 figured out, you're probably doing pretty well with this. But if anybody tries 1 or 2 or 3 or just wants to see the answers, I'll probably put up the answers to a few of those after like 5 or 10 minutes, just so you can see if you're on the right track with those. So if anybody on the Zoom has questions, let me know. If you want to stay on, I'll probably put up the answers to these in like 5 minutes. You can see if you got the first ones figured out. And then I'll stop the recording. But